Alright, so these are going to be our notes on circular motion. It's a new topic we started to cover in physics. And these are going to be kind of your introductory notes that kind of explain the basic concepts of what we're going to be talking about for the next week or two. And our whole goal is really to get to the idea of gravity and Newton's universal law of gravity. And to understand that law, we have to understand the basics of circular motion. So if you see here, circular motion is really, let me just change this. Circular motion is just really motion around a central axis. So if you think of a Ferris wheel, like if we had a axis, or we have a wheel in a, just go with a wheel for a car, or even a wagon wheel would work. Hopefully I can do this all right. Okay, so we have this wagon wheel and it's going to turn this way, right? And if we think about this motion, really there's a central axis. This is really a simple machine, by the way. And that motion goes around this central axis. Okay, so anytime we see something that has an axis like this and everything's rotating around the outside, that's circular motion. And we can even say a Ferris wheel if we had the cars on here, people riding in them. And this would also be circular motion as the cars go around, this rotating around this central axis. Now, there's something that's very important to understand about circular motion, and what really is going to drive our understanding is this idea of being uniform. Okay, and uniform means velocity and acceleration is constant, means no change. So that means these are objects that are rotating around a central axis at a constant speed. So, and really not constant acceleration. I think that's a misnomer. Constant acceleration would be constantly getting faster and faster. It's really kind of not a good way to look at it, but constant velocity is really, make sure you remember that. Okay, so the acceleration part of it, though, that we want to remember, it's really when we look at the velocity is constant. So that means it's not accelerating. But there's more than one type of acceleration. Another type of acceleration is where this car here on this Ferris wheel, the velocity at one point is going this way, but then if this is the same car, this car would then be velocity would be this way. So then there's a change in the direction of velocity, and that's where we get the acceleration. It's a different type of acceleration because velocity is not changing, so there is no increase or acceleration. Okay, but the acceleration we talk about for this is a change in direction. And when it gets over here, it's going to be going this direction, and so on here, it's going to be going this way, and so on. It just keeps changing as it goes around. And that is the constant acceleration. Okay, now we can take this motion and we can describe it in a lot of different ways. The first one here is tangential speed. Tangential speed, as you see here, is the speed of any object at any point along the circular path. Okay, so if we just, right here at this second that this car is moving this direction, let's make it a little bit bigger. So right here, this car is moving this direction on the Ferris wheel, and if we measured this speed in this moment in time, we would call that tangential speed. Okay. Now, something really important to remember is that tangential speed really depends on the distance the object is from the radius, especially when velocity is constant. Because if, let's just draw a CD for a, it's not a very good circular one, but if we got a CD for a music CD from whoever the Rihanna or whoever those rock stars are these days, or hip-hop, whatever they're called. But if this was a CD and there just happened to be a bug standing right here, then there was another bug really close to the central axis. As these then move around, we'll make this a different color actually. As this orange one moves around, for it to make one revolution, it travels that far. And then this pink one though, if it's, directly across from it, so on, for this to move around, look how much further it has to go. Okay, so with that thinking, you have to realize that this one on the outside has to move faster than the one on the inside. So depending on how far you are from the radius, that will cause your speed with uniform or uniform velocity to be greater. So if you're a bug right here, you're not going as fast as the bug that's out here because you have to be in the same spot at the end. Okay, so that's kind of something to remember about tangential speed. Now, and what it means about distance from the radius. Now this is the equation, v of t equals centripetal acceleration times r, but you have to remember originally this was a squared. We remove the squared and we make it the square root of this. That will then give us the answer. Now in lab we're going to look at something a little different, maybe a little bit of a different equation, and I think it'll help you maybe grasp it a little bit easier. But initially we're going to use this equation. It's pretty standard. So that's tangential speed. It's one way you can describe an object that has circular motion. So now I'm going to erase this. If we keep going, we can also say another thing called centripetal acceleration. And centripetal acceleration is acceleration due to a change in position. And I had talked about that before when I was talking about circular motion. So we have this, it's a horrible circle. Let's start over. Try to do my best here. It's hard to draw with this mouse. I'm going to go with orange. Okay, come on, give me a nice circle. Not too bad. Okay, so we have I don't know, a bug. Or we'll actually just say a car. A Ferris wheel car. Like we talked about before. So we have these little cars on a Ferris wheel. And we'll just say it's the same car, different time. So hopefully you've been on a Ferris wheel and you kind of know what I'm talking about. You go to the fair, you get on this thing. They come around, pick you up, put you in the cars and make it go around. Now, if this was moving at a constant velocity, so let's say velocity t doesn't change, and it's always 15 meters per second, and it's constant, c. So then you would think there's no acceleration, right? But as we were talking about before, this car at one moment in time has gone that direction. At another moment in time, it's gone that direction. At another moment in time, it's gone that direction. And another moment in time, it's gone that direction. Okay, so and if we want to calculate it, all we need to know is this equation right here, a of c vt squared divided by r. Now, this one isn't as useful actually, because really the direction is, this acceleration is due to a change in direction. Okay, it could be, maybe we won't go there, but so this is a change in direction. So this is going northwest, right? Now it's going southwest. Now it's going southeast. Now it's going northeast, right? Okay, at a certain angle. So it's constantly changing. There is an equation for it, but the main important idea to understand with centripetal acceleration is the idea that it's a change in position, not necessarily a change in velocity. Okay. Then the other one comes in where tangential acceleration is acceleration due to a change in velocity. Okay, this is really the same as straight line acceleration, and if you remember the equation, we'll use blue here. So A is Vt, velocity final, minus velocity initial, divided by the change in time. that would be how we'd figure this out, because let's say the car was right here and it was moving at 10 meters per second. And then right here they're slowing it down to let new people on, and right here it's moving at 5 meters per second. So then we would just say, and if this took time is 2 seconds, we would just plug into this equation. 5 minus 10 is -5 divided by 2, -2.5 meters per second squared. That'd be the acceleration tangential. Okay. So, and this can be decelerating like it would be here, and it'd be a negative number. It could be accelerating, going faster, and it'd be a positive number. And that's tangential acceleration. And the thing to remember as well is these can be at the same time, because this is changing direction as well. So 10 meters per second southeast, 5 meters per second, still kind of southeast, but a different angle. So we got an angle here, right, from Infoot's center, right? So we got this angle, then we got this angle, and these thetas are different. So then that's really a different direction. So we have this occurring at the same time. Important to remember that. Okay, and the last thing we want to worry about here, I'm going to erase this, so get ready. Goodbye. And the last thing is this thing about centripetal force. So centripetal force now is talking about force is a mass times an acceleration. So if you know the mass of something and you know its acceleration, you can figure out the force that's acting on it. So here, a force causes change in motion, right? So change, we're just going to put change. And so we can look at that centripetal, and if you remember up to centripetal acceleration, that is acceleration due to a change in position. So this is a force that causes an object to accelerate like this centripetal acceleration, but it causes circular motion. So this is causing it, you know, like if you had a sling, piece of rope, and you tied it around a rock, just tie it around here, okay, and then you swung this thing around in a circle, like David and Goliath and so on, and so let's put a person in here. So he's going to circle this thing around, and as he does, as you do that, if you've never noticed this, you actually have to apply a force towards you, okay, towards yourself, and that's centripetal force. And that causes this circular motion, because as this thing's going, you have force like this, okay, but then you have this force that you're applying to it, and when you determine the vectors back out, it's going to be more like this. And when it gets over here, you have the force in, you have a force going this way, so as a result, you have this vector force, and that causes the circular motion. Now the equation for this is F of c is mass, that's m, times v of t squared divided by r. And it's the more complicated calculations, and just like in linear motion, a force, this is going to be a Newton, N, tangential acceleration, meters per second squared, and then if it's velocity, it's going to be meters per second or kilometers per hour, but those kind of units. Then the only other thing we really got to talk about, and it's not exactly on here, but we should probably talk about it, is the idea of centrifugal force. I'm just going to type this in there real quick. And centrifugal force is talking about the force as you have that thing going around, or if you've ever been on a Ferris wheel or the hellhole thing, where it feels like you're being pushed out. Okay, and really centrifugal force is just really demonstrating to you this idea of inertia. It's really not there. It's not really a force. It's really just inertia. So as you're on a Ferris wheel, and this is going around, say it's going really fast. or roller coaster or whatever, and you're in a car. It's one of those ones that's enclosed, so it goes really fast so you won't fall out. Okay. But as you're moving this way, and your whole body and your weight, there's a tendency to resist the change as you're going to have to start going this way. And that's inertia. And the inertia makes it feel like there's a force on you pushing you out this way, but really there's not. It's just the inertia, and you have to the force has to overcome that inertia and cause it to move this way. And it just keeps, and as you're going this way, then you want to continue moving that way, but then the force causes you to move that way, and that's inertia. All objects tend to resist a change in motion, Newton's first law. And that's centrifugal force. And that's our first notes. Hopefully this makes a lot of sense to you, helps you understand what we're doing in class, and let me know if you have any questions.